Welcome to Earthly Teachings. Today, we begin our study of Electrotechnics N4. Our focus will be on the construction and operation of single-phase transformers. Transformers are fundamental devices in any power system, and by the end of this lesson, you will be able to, first, define what a transformer is and explain its purpose. Second, identify and describe its main components. Third, understand how a transformer operates both with and without a load connected. And fourth, explain the cooling methods used in transformers to maintain their performance. Let's dive in. First, let's start with a clear definition. What is a transformer? A transformer is an electrical device used to change the AC voltage. This is a key point. It works only with alternating current. It can increase the voltage, which we call stepping up, or decrease it, known as stepping down. There's a crucial relationship here. If the voltage increases, the current decreases, and vice versa. Power is transferred, not created. It transfers power from one circuit to another through a process called electromagnetic induction, without any electrical connection between the two circuits. In essence, a transformer is an AC voltage and current converter. Let's repeat that for clarity. A transformer is an electrical device that uses electromagnetic induction to transfer power, stepping up or stepping down the AC voltage while doing the opposite to the current. Now let's explore the physical structure of this device. We'll be looking at the construction of a transformer. A transformer is built from two main components, a core and windings, as shown in this diagram. First, the laminated iron core. This is not a solid piece of iron. It's made of thin sheets of steel, called laminations, stacked and insulated from each other. Why? To reduce energy losses, which we'll discuss later. This core is made from silicon steel. Silicon steel is chosen because it retains very little residual flux and has a very low reluctance. Reluctance is the opposition the core presents to the flow of magnetic lines of flux. A low reluctance is good, as it means the core efficiently guides the magnetic field. Second, we have two sets of windings. They are typically made of insulated copper wire. The primary winding is connected to the AC power source. The secondary winding is connected to the load. There is no direct electrical connection between them. So, to recap, the core provides a low resistance path for the magnetic flux, and the windings are the coils that create and are affected by this flux. Now that we know the components, let's see how they work together. We'll begin with a transformer operating at no load, also known as an open circuit. In this state, as shown in Figure 4.3, an alternating voltage V1 is applied to the primary winding. Notice there is no load connected to the secondary side. This alternating voltage causes a small current called the no-load current I0 to flow through the primary winding. This no-load current has two main components. One component creates the magnetic flux, and the other supplies the losses in the core, like eddy current and hysteresis losses. The no-load current I0 produces an alternating magnetic flux, represented by psi, in the primary winding. The laminated iron core is designed to channel this magnetic flux. The flux path is almost entirely contained within the core, and it passes through both the primary and secondary windings. Because the magnetic flux is alternating and passes through the secondary winding, it induces an electromotive force, or EMF, in that winding. We call this E2, the secondary open circuit voltage. This entire process, where a changing current in one coil induces an EMF in an adjacent coil through a common magnetic field, is called mutual inductance. This is the fundamental principle of transformer operation. Now, let's connect a load to the secondary side and see what happens. This is called operating the transformer on load, or a closed circuit. As you can see in this new diagram, Figure 4.4, a load has been connected to the secondary winding. Remember the induced EMF, E2? Because the circuit is now closed by the load, this EMF drives a current, I2, through the secondary winding and the load. This secondary current is the output of the transformer and delivers power to the load. You'll also notice the current in the primary winding is now labeled I1. This is the current drawn from the supply to deliver the power required by the load. Furthermore, the secondary current I2 and the load impedance create a voltage drop. As a result, the voltage available at the load's terminals, which we call V2, is slightly less than the induced EMF E2. A crucial concept to remember is that the energy transfer from the primary winding to the secondary winding is done entirely magnetically, via the common flux in the core. There is no electrical connection, only magnetic coupling. So we've discussed the basic operation. What if we imagine a perfect world? Let's consider the concept of an ideal transformer. An ideal transformer is a theoretical device that operates with 100% efficiency. This means it has no losses. It implies that the power put into the primary winding, P1, is exactly equal to the power delivered to the load by the secondary winding, P2. In other words, the power input is equal to the power output. This is a simplified model that helps us understand the fundamental voltage and current relationships. However, in practice, we do not find ideal transformers. Real transformers, like all electrical devices, experience losses. Losses mean that some of the electrical energy is converted into heat and is not available at the output. This conversion of energy into heat during a process is generally referred to as a loss. These losses, in the form of heat, reduce the transformer's efficiency. We will learn more about the specific types of losses, such as copper and iron losses, in a later unit. One of the most significant sources of loss in a real transformer is eddy currents. Let's discuss eddy currents in detail. The iron core is designed to channel magnetic flux. In an ideal world, it would not carry any electric current itself. But that's not what happens in reality. The alternating magnetic flux in the core, the very flux we use to induce EMF in the secondary, also induces a small EMF in the core material itself. Because the core is a conductor, this induced EMF causes currents to flow. These currents don't follow a winding. They circulate in closed loops within the core, much like eddies in a stream of water. They are known as eddy currents. As these eddy currents circulate, they encounter resistance in the core material. This resistance converts electrical energy into heat, causing the core to get hot. This heating represents wasted energy, which we call eddy current loss. It reduces the transformer's efficiency. To minimize these losses, manufacturers take two key steps. First, they use silicon steel, which has a higher resistivity than pure iron. Higher resistance means smaller currents. Second, and this is why we have a laminated core, they laminate the core. By dividing the core into thin, insulated sheets, we break the path for large circulating eddy currents, forcing them into much smaller, weaker loops, which significantly reduces the heat generated. Because of eddy currents and the current flowing through the windings, transformers generate a lot of heat. If this heat builds up, it can destroy the transformer's insulation and cause a catastrophic short circuit. Therefore, cooling is absolutely essential. Transformers must be cooled. There are several methods for cooling transformers, which can be used individually or in combination. The methods include natural air cooling, forced air cooling, and various types of oil cooling. Let's start with natural air cooling. This is the simplest method, suitable only for small transformers. As seen in Figure 4.5, there are no fans or pumps. The heat from the windings and core simply radiates into the surrounding air, which then rises and is replaced by cooler air. The process is entirely passive. For larger transformers, we need more active cooling. Forced air cooling uses fans to move air more rapidly over the transformer's surfaces, which can be the windings and core in a dry-type system, or the cooling fins of an oil-cooled transformer. You've likely seen large industrial transformers with rows of fans attached to their cooling fins, just like the one in Figure 4.6. This method greatly increases the rate of heat dissipation. Next, let's look at cooling methods that use oil, which are very common for medium and large transformers. These methods are broadly referred to as oil cooling. In these systems, the entire transformer is placed inside a housing called the transformer tank, which is then filled with a special type of insulating oil known as transformer oil. This oil serves multiple critical functions. Let's list them. First, it acts as a secondary insulator, adding to the insulation of the windings. Second, the oil prevents arcing. An arc is a powerful electrical discharge that can occur between high voltage points. The oil's insulating properties stop this. Let's define arcing. Arcing is the formation of an electric arc when electricity flows or discharges along an unintended path. Third, and this is its main job in cooling, the oil serves as a coolant. It absorbs the heat from the windings and the core. Fourth, It provides a barrier between the paper insulation of the windings and atmospheric oxygen. This prevents the oxygen from degrading the insulation. Let's look at the most common type of oil-cooled transformer. This is the oil-immersed air-cooled transformer. Figure 4.7 provides a detailed diagram of such a transformer. Let's trace the cooling process. The process starts with the windings and core generating heat. Step 1. This heat is transferred to the transformer oil surrounding the components inside the tank. Step 2. As the oil gets hot, it becomes less dense, expands, and rises. This heated oil flows up into the cooling fins, which are visible on the sides of the transformer tank. Step 3. The cooling fins are designed to have a large surface area. Here, the heated oil transfers its heat to the cooler ambient air through the fins. Step 4. As the oil cools down in the fins, it becomes denser and sinks to the bottom. It then flows back into the main transformer tank, where the cycle of absorbing heat and circulating repeats. This process is a continuous natural convection cycle, effectively and safely removing heat from the transformer. Beyond cooling, transformers have several vital accessory components that ensure their safe and efficient operation. Let's examine the first, the conservator tank. As we just discussed, the transformer oil heats and expands. If the tank were completely sealed, this expansion would create immense pressure, which could damage or even explode the tank. To prevent this, a smaller conservator tank is mounted above the transformer's main tank. Its function is to provide extra volume to accommodate the expansion of the oil. Next is the breather, which works in conjunction with the conservator tank. As oil expands and rises into the conservator, it pushes air out. As it cools and contracts, it draws air in. But this air can be moist. Moisture is a transformer's enemy. It degrades the oil and insulation. The breather's job is to ensure that any air entering the conservator tank is completely dry. It does this using a chemical called silica gel. Silica gel is a desiccant, which means it absorbs moisture. New silica gel is blue. As it absorbs moisture from the air, it turns pink, indicating that it's saturated and needs to be replaced or regenerated. The oil cup at the bottom of the breather prevents the oil inside the transformer from coming into direct contact with the atmosphere. Finally, for large and valuable transformers, a sophisticated protection system is used. This is the Buchholz relay. A Buchholz relay is an oil and gas-activated protection relay, as seen in Figure 4.9. It's used to protect large transformers, typically those bigger than 500 kVA, from internal faults like overloads and short circuits. It's located in the pipe that connects the main transformer tank and the conservator tank. The relay works by detecting gas production, which is a symptom of internal faults. Gas bubbles are produced when the transformer oil overheats. Let's consider an overload. An overload causes the oil to overheat and decompose, producing gas bubbles. These bubbles travel up to the relay. In the relay, these bubbles accumulate in the chamber and displace oil. The rising oil level lifts a float, which activates a mercury switch. This switch closes an alarm circuit, warning operators of a potential problem. Now, what about a more serious fault, like a short circuit? A short circuit produces a very large volume of gas very quickly. This causes a sudden rush of oil into the relay chamber. This oil surge lifts a flap, which activates a second mercury switch. This switch is connected to the tripping circuit, and it immediately disconnects the transformer from the power supply, preventing further damage. The Buchholz relay is a crucial safety device, providing early detection and protection against internal transformer faults. Finally, for the very largest transformers, oil-immersed air cooling is not enough. They require an even more active and powerful cooling system. This is the oil-immersed water-cooled transformer. Let's trace the heat flow in this system using Figure 4.10. Here, the heated transformer oil is not cooled by air, but by water. A pump circulates the hot oil from the top of the transformer tank through an external device called a heat exchanger. In a heat exchanger, the hot oil and cold water flow on separate, isolated paths, but in close proximity. The heat is transferred from the hot oil to the cold water. The newly cooled oil is then pumped back into the bottom of the transformer tank. At the same time, cold water from an external source, like a cooling tower, is pumped into the heat exchanger. It absorbs the heat from the oil and leaves the exchanger as hot water, which is then sent back for cooling. This closed-loop system is highly effective for removing large amounts of heat, but it is also more complex and requires more maintenance. Let's quickly review the key concepts we've covered in this lesson. We started by defining a transformer as a device that changes AC voltage and current using electromagnetic induction. We learned about its essential parts, the laminated iron core and the primary and secondary windings. We saw how it works at no load, inducing an EMF and on load, delivering current and power magnetically. We discussed how eddy current losses are reduced by laminating the core and using silicon steel. And finally, we detailed the various cooling methods, from natural air to oil-immersed water cooling, and the vital components like the conservator tank, breather, and Buchholz relay. Understanding these principles is crucial for working with transformers in any electrical system. Thank you for watching Earthly Teachings. Subscribe for more Electrotechnics N4 tutorials and revision lessons. We'll see you in the next video.